So I'm going to go over this week 8 material. It starts with electron dot formulas and then goes into predicting the shapes of molecules and the polarity of molecules. And because they're all interrelated and in this assignment, after you've done the Lewis dot structure, then it says to do the shape of molecules for the same ones and then the polarity of the same ones. So it actually makes sense to just all at once do all three of those for each of these. So I'm going to start with F2, which is fluorine gas. And the steps for what you do are listed here, but they're not explained in detail how you do them all. So for the first step, counting the valence electrons in all atoms, that means how many valence electrons are there in 2 fluorine atoms. And so to know how many there are, we need to know how many are in 1, and then we just multiply that by 2. So fluorine, the way you know how many valence electrons anything has is you find it on the periodic table, and then whatever the number is up here for that group, in this case it's Roman numeral 7. If you're not comfortable with Roman numerals, you can just write the regular number up on top for reference. But so this means that fluorine has 7 valence electrons. And all the ones that you're going to be given are going to be over here plus hydrogen. You're not going to ever be given any of these transition metals, or these for that matter. So you don't need to worry about the ones with the B. So it's just the ones with the A that you're going to be looking at. So fluorine, each fluorine has 7, and so I'm going to write that on. So for F2, we just have 2 times the number of valence electrons that each fluorine has, which is 7. So that means we have a total of 14 electrons. And that's how many total electrons we have to work with here, and I'll show you what we're going to be doing with them. And I'm just putting the E with the negative sign, that's just to indicate electrons. And I apologize for my terrible handwriting. I'm writing with a mouse here. So hopefully it's all at least legible. So in this case, if you only have 2 atoms and they're bonded together, then there's only one way they could possibly be bonded together, which is side by side with a bond in between. And we're always going to start with a single bond. So you'll just represent that by a line. And what that is made out of is 2 electrons. So just by drawing this line here, we're using up 2 of our 14 electrons. So we just want to keep track of how many we have to work with, how many we've already used. So now we're down to 12 electrons. We've used 2 of them to make that single bond between the fluorines. After that, what we want to do is we want to give, if possible, we want to give each atom in the molecule a total of 8 electrons. Unless it's hydrogen, hydrogen only gets 2, but we don't have that here. We will in a future one. So we're going to give it a total of 4 electrons, and I'm just going to make this a little bit bigger so I can make nice dots. And so this fluorine wants to have 8, and this fluorine also wants to have 8, but this bond that's right here represents 2, and so that counts as 2 for each of them. They're sharing those 2 electrons. So we've already got 2, and now we're going to add them until we get 8, and we're going to add them in pairs. So we've got 2, 3, 4, 5, 6, 7, 8. And so this one now has 8, but we only used another 6 electrons because this one we'd already counted for when we went from 14 down to 12. And so from 12, now we're down to 6 electrons, which is just perfect because that's how many we need to put over here. And so now we've used up all 14 of our electrons. 2 of them are here in this single bond, and the other 12 they're called lone pairs of electrons around the outside of the fluorine. And so that we've exactly used up all of our electrons, which is what we need to do at the end of this. And we also have given each atom what's called an octet of electrons, which means there's 8 around it. So for this one, the 8, you could circle it here and say, okay, here are the 8 electrons for this fluorine, 2, 4, 6, 8, and then the 8 electrons for this fluorine, 2, 4, 6, 8, because these two get shared between the 2 fluorines. Then for the next step, which is the shape of it, so that's it. This is the Lewis structure right here. That's finished. So if you just have to do the Lewis structure, you would just get to there and you'd be done. If it wants the shape of it, then you'll use this molecular shape and polarity table, which I really like. And you'll see just visually which one looks the most like what you have. And the only one that only contains 2 atoms in it is this image right here. So this is representing one fluorine and the other fluorine. And so the shape then is called linear. So that's it for finding the shape. That's all you have to do for this one. If it is also asking for the polarity, then go down here to the polarity. And polarity means, does it have a plus and a minus end, or is it evenly shared, plus or minus? And so nonpolar means it's evenly shared. So it's an atom is nonpolar in this case if A and X are the same. We're calling AX the formula here. So in this case, our formula is F2, which means that the A is F and the X is also F. So they're the same, and that means this example is nonpolar. If it had been an F that was bonded to an H, for example, then they'd be different, and then it would be polar. The example here is H2 is nonpolar. That's a lot like our F2. And HCl would be polar because the H and the Cl are 2 different elements. So that's it for the F2. Nothing too tricky there. And let's see, I'm going to go back to the problem. So we'll go to the next one. We've got CH4. And so I'm going to clear the board and show that example. Oh, actually, I'm not yet. I'm going to show you one other thing first. And this is something that will calculate or produce the Lewis structure for you. And it's Wolfram alpha, and probably the easiest way to find it is to just type in Wolfram, which is like wolf, like the animal, followed by ram, like the animal, and then type in Lewis, Lewis, structure. And for me anyway, this is what shows up as the very first result. And it'll look like this. And so just right here where it says molecule, if we typed in F2, and you have to use capital and lowercase letters correctly in that box there so it knows what molecule you're talking about, and submit. And look, it's just like what we had. The 2 F's connected with a single bond, and then 3 pairs of electrons around each fluorine. So this, I was trying it out on the ones in this homework assignment, and it worked beautifully for all of them except for SO2, unfortunately, and I don't know why it's not working well for that one. But for the most part, it works, and it gives you a really nice Lewis structure. Okay, so now we're going to go to CH4, and so we're going to start out with the same thing as last time, where we're going to count up how many valence electrons we have. So in this case, we have a carbon and 4 hydrogens, and I'm going to write them on different lines here. And then I'm just going to go to my periodic table and check and see how many valence electrons each of those has. So if you have different elements in it, you're going to have to figure it out for each one, and then it's multiplied by how many of them there are. So carbon has 4 valence electrons. Hydrogen has 1 valence electron, but we have 4 hydrogens. So for this, it's going to be 1 times 4, which of course equals 4. And then we're going to add these 4 from the carbon, these 4 from the hydrogen, for a total of 8 electrons available in CH4. And now we need a starting point for what the structure looks like. In the instructions here, it says make the structure, usually the central atom is the one closest to the center of the periodic table. I've got a couple other tips for you. If carbon is there, it's pretty much always the center, and in this case we have CH4, so we can put C in the center, and then we're just going to attach the 4 hydrogens to it. Another rule is that hydrogen can never be in the center, and another kind of rule of thumb is if you have only one of a certain element, that's usually in the center. So I'll show you how that applies to some of these other ones. So here you've got a carbon, and so you're going to put carbon in the center. Here you don't have a carbon, but there's only 1 nitrogen and 3 fluorines. So there you put nitrogen in the middle, put the 3 fluorines around it. For F2, O2, and N2, it doesn't matter. They're just going to be side by side, like with the F2 that we already did. CO2, you've got a carbon, so that goes in the middle. I'm skipping these 2 that have 2 carbons because there it's a little bit different. There's not a single thing in the center. Here we've got a carbon, so it goes in the middle and the 3 oxygens go around it. And here we put the sulfur in the middle because it's the one that there's only 1 of, and then we're just going to put the 2 oxygens side by side on that. In the other examples over here, this also works. Here we've got a carbon, so it goes in the middle. Carbon, it goes in the middle. No carbon, but there's just 1 oxygen, so it goes in the middle, and 1 hydrogen on each side of it. No carbon, but we have just 1 phosphorus, so the 3 chlorine, phosphorus goes in the middle, the 3 chlorines go around it. Here we've got a carbon, so it goes in the middle, and here there's no carbon, but there's just 1 chlorine and 3 oxygens, so put your chlorine in the middle, put your 3 oxygens around it. So those 2 rules will usually get you what you need to know, and we'll do an example of one of these 2 with the carbons in it, so I can show you what to do in that case. So, okay, so we've drawn it, and remember that these lines each contain 2 electrons. So we've already used up 2, 4, 6, 8 electrons. That's all we have. We have run out of electrons, but luckily this is already done because I think I mentioned earlier, hydrogen is the one element that doesn't want 8 electrons. It only wants 2. And because these two are shared with everything, that means this hydrogen has 2, and each of the hydrogens, of course, they're all the same, they have 2. And the carbon, because these are being shared, the carbon has 2, 4, 6, 8. So the carbon has 8 just like it wants to have. So everything's perfect in this one and we're all good. We can go into the Lewis structure thing to make sure we're going to get the same answer that we got there. And so type in CH4 and let it do its thing, and it's the same thing, it just is like at a different angle. But carbon in the middle, 4 hydrogens around it, and no lone pair electrons anywhere. Then when we go to the next step to figure out what shape it is, this one's a little more complicated, but you can already see right away that it's going to be this one because it's something in the center with 4 things attached to it. So that they're calling it AX4. What that means is you've got A is whatever's in the middle, and then 4 somethings attached to it. They don't necessarily have to be 4 of the same thing attached to it, but in this case, they're 4 hydrogens. And then no electron pairs, which is, in this case, what it means is no electron pairs on the central atom. If we'd had some electron pairs, if this wasn't hydrogen, if it was, say, fluorine, it would still have electron pairs around one of the things attached to it, but there just wouldn't be any electron pairs on the central atom. In this case, that's carbon. That shape is called tetrahedral. And then to get to the polarity, it's similar to what we did down here with the F2 example. It's nonpolar if all of the X's are the same. So right now we have all of our X's are hydrogen, so that means it's nonpolar. It would be polar if any of them are different, and so the example here, CH4 is what we have, and that's the example on here for nonpolar. CH3Cl is polar, and that would be, this would be a carbon in the middle. 3 of these light blue atoms would be hydrogen, and 1 of them is chlorine. So any of them being different from each other would make this polar. So it could be 1 hydrogen and 3 chlorines, or 2 hydrogens and 2 chlorines. Any combination like that is going to make this whole molecule polar. Okay, so then on to the next one, which is NF3. So again, we're going to clear the page, draw in Rn, and then our F3. We're going to check and see on the periodic table how many valence electrons we have for each of those. So nitrogen's here, it has 5. Fluorine is here, it has 7, but there are 3 of them, so 7 times 3. So we'll write in the 5 here. And then we have 3 fluorines. They each have 7 electrons for a total of 21. Add the 5 and the 21 together, and you have a total of 26 electrons to work with. Because NF3, there's 1 nitrogen and 3 fluorines, we're going to put the N in the middle. And then we're going to attach that with single bonds to fluorine and fluorine and fluorine, and it doesn't really matter how you space out the fluorines. Because right now we're just guessing at the structure. We don't know exactly what the shape is going to be. That comes after we get the Lewis structure down and then check the table. So how many electrons did we use up just in our starting structure? We've got 2, 4, 6 here that we've already used up. So just to keep track of how many we have, we're going to subtract those 6 and keep a running total of how many we have available. So we have 20 electrons left, and then we want to give, so now this is a little bit different. Now we have to know where we're going to start putting those 20 electrons. The easiest way to do that is start putting them on the atoms that are on the outside instead of starting with the central one. And again, like we did with the F2, we're just going to add electrons until each of these fluorines has 8. But they're all starting out with 2 from this, 2 shared electrons from the bond. So we've got 2 here, 3, 4, 5, 6, 7, 8. And then it's going to work the same for all of them. Okay, and so to get it here, we've used up 2, 4, 6, 8, 10, 12, 14, 16, 18 electrons. So now we only have, subtract out the 18 that we've used. So now we have 2 left. So now what do? We need to check the center atom now and see if it has an octet. And so far all of its electrons are coming from the 3 bonds. So it has 2, 4, 6, and we've got 2 left. So that works out beautifully. So we add those here and here. Now we've used up all the electrons, and now just to double check, we want to make sure that everybody has 8 electrons and that they're all happy. So the fluorine has 2, 4, 6, 8. This fluorine, of course, all the fluorines are the same, 2, 4, 6, 8, and 2, 4, 6, 8. And the nitrogen has 2, 4, 6, 8. So everybody has an octet, and we've used up exactly all 26 electrons that we started with. So that is how we know that we're done with the Lewis structure, and then we want to see what this gives us, NF3, double check our work. And indeed it gives us, and again the shape is a little bit different. They've got these going off at different angles. That does not matter. You're not going to be graded on what angles you put those out at, and so that isn't important. But so basically this is the same Lewis structure as this one. The important thing being these 2 lone pair of electrons on the central atom, which is the nitrogen. And so that's going to be important now when we come over to the shape and polarity table. So now if we look here and here at the same time, we've got a central atom and we've got 3 things attached to it. So looking over here, that could either be this one or this one, and we need to figure out which one it is. So this is AX3, which means that the central atom A, which in our case is nitrogen, has 3 bonds and no electron pairs. We have a central atom with 3 bonds, but we also have an electron pair, and that's very important here. That is, here, let's color red. that is not what I meant to do. Undo. I just want to draw a red circle around these. So that is your lone electron pair. These are your bonds. 1, 2, 3 bonds. And 1 electron pair. So that is A for the center, X3 for the 3 bonds, E for the lone electron pair. So that's actually what we have here. If I were you, I would take this and draw an electron pair, just 2 little dots above the dark blue center atom here. And that will remind you that this is what you have if you have an electron pair here. And so that shape is called trigonal pyramidal. And for polarity, we don't even have to think. It's just polar. So that's nice. And the example NF3 is what we have. And so the interesting thing here is that this shape is a little bit different than this one here. This is what you would get if there were no electron pairs and you had 3 evenly spaced things attached to it. I'm not sure if we'll have one of these in this example. This is the one I call a fidget spinner, where if you set it down, it would spin on this central atom. But this one, hopefully you can tell by how it's drawn here that these are down at a little bit of an angle. And that's because they're kind of getting pushed down by the 2 electrons here. And that's why those 2 electrons change the shape from between trigonal pyramidal with the electrons or trigonal planar without the electrons. And there's another way I can show you the shape. And this is something you could try also if you like. It's molview.org, MOLVIEW. When you first pull it up, it's going to have this complicated structure in it, but we are looking at, what is it, NF3. And so right here in the search bar, we can just type in NF3 and enter, and it'll show us. The downside to this is it's not a Lewis structure. It does not have the dots around the fluorine or the lone pair dots on the nitrogen. So don't use this as your guide for a Lewis structure. You have to go with that Wolfram one for that. But what you get over here is an actual 3D model of it. And so you can move that around. You just click it with your mouse and drag around. And so you can see with that that it's a little bit, that these, the green fluorines are down at a little bit of an angle from the nitrogen in the middle. And I think BF3, I'm going to give this a try. I think BF3 is trigonal planar. So that would be this one here. And so if you tilt that one, if we hold it like that, you can see that they're all on the same plane. And so this is the fidget spinner type molecule. So that's the difference between trigonal planar and trigonal pyramidal. This one, trigonal planar, is the fidget spinner, and trigonal pyramidal is the one that has a lone pair of electrons in it. So then, what do we have next? Oh, okay. So C2H6, that's another good example to do. Okay, so we're going to clear this. And so C2H6, C2 from the periodic table, we already know carbon is 4. Whoops, let me go back to black. Carbon is 4, so 2 carbons are going to have 8 electrons, 2 times 4. and H6. Each hydrogen has 1 electron, so 6 hydrogens have 6 electrons. So we've got a total of 14. Whenever you have something with more than 1 carbon in it, then those carbons are going to be all lined up in a row. So in this case, just carbon next to carbon. And then you put the hydrogens around it evenly. So since we have a total of 6 hydrogens that go on the 2 carbons, we're going to put 3 hydrogens on each carbon. There's another one later in this homework that's C2H4, so in that case you just put 2 hydrogens on each. And hydrogen, and here we go. Okay, so the first thing we need to do is count up how many electrons we've used just with the single bonds. And each one is 2, remember. So we've got 2, 4, 6, 8, 10, 12, 14. And guess what? 14 is how many we have available. Hydrogen doesn't get any lone pairs of electrons, it just gets a single bond, so it's good. All the hydrogens are the same with just a single bond, so they're all happy. And the carbons each have 2, 4, 6, 8. 2, 4, 6, 8. So the carbons are good because they have their octet. So this one is done. This one is a little bit different for the shape because you have to have a central atom to call it a shape. So in this case, each central atom has 4 things attached to it, even though one of those things is this carbon, which itself has things attached to it. So basically this just ends up being AX4, which is tetrahedral. And so what you would really say is that this carbon is tetrahedral and this carbon is also tetrahedral. And since everything attached to it is hydrogen, so they're all the same, then it would be nonpolar. If any of these hydrogens got changed to, say, fluorine or chlorine or some combination in there, then it would be polar. So that rule works the same way for this one. And I am going to stop here because I've been going on a while. Oh, actually I'm not, because there's one important thing that has not come up yet, which is when you make double bonds. So I'm going to use CO2 for that example. So we're going to clear this out. CO2, we've got carbon has 4, and oxygen, I need to double check. Oxygen has 6, and we had 2 oxygens. So 2 times 6 is 12. And that's got CO2, so there were 2 oxygens there. Add those together. 16. Since CO2 has a carbon in it, we're going to put carbon in the middle. We're going to attach an oxygen on each side. So now we've used 2, 4 of the electrons to make those 2 bonds. So we'll subtract those, and now we have 12 left to put on the oxygens. And so again, we're going to start with the ones on the outside, not start by putting electrons on the carbon. And so to get oxygen 8, we've got 1 right now. So we've got one bond, so we've got 2 electrons. We've got 2, 3, 4, 5, 6, 7, 8. So now we've used up 6 of our 12 electrons, and then we'll do the same over here. 2, 3, 4, 5, 6, 7, 8. Okay, so out of our 12 remaining electrons, we've used up all 12 of them. So you'd think you were done there, but you're not, because the carbon only has 2, 4, and it needs 8. So then what do we do? Because we're out of electrons, we don't have any more that we can put here. But what we can do is move some of these lone pairs of electrons and make double bonds. And that will mean that the oxygens and the carbons are sharing electrons that they weren't sharing before. So what we're going to do here is every 2 electrons could also be a bond. So we're going to erase those 2, and then we're going to draw a new, make this from a single bond into a double bond. So we took away 2 lone electrons, and then we added another bond, but that bond also uses 2 electrons, so we did not use any additional electrons when we did that. And so now this oxygen still has 2, 4, 6, 8, and the carbon now has 2, 4, 6, so it's getting better, but it still doesn't have 8. So as you've probably guessed, we need to do the same thing over here. Sometimes you're only going to do it to one or the other, but in this case we're going to do it to both. So we're going to take away these 2 electrons and then make this into a double bond. So now everything's good. We've got our oxygen 2, 4, 6, 8, our carbon 2, 4, 6, 8, and our other oxygen 2, 4, 6, 8. And we can plug that in here. CO2. And we get the same thing, just a slightly different angle. But the important thing here is we've got the oxygen, 2 lone pairs of electrons, a double bond, the carbon in the middle, another double bond, and the other oxygen also has the 2 pairs of electrons. So to complete this, now we will go to the molecular shape and polarity table, and this looks like this one. And the only one you might confuse it with is this one, but it's different because this one only has 2 atoms in it and this one has 3. So it's AX2. Oh, you could also possibly confuse it with this one, so I'll tell you what the difference is. AX2, this one has no electron pairs on the central atom. It does have electron pairs around the oxygen, but that's not what this is referring to. You just look at the central atom, the carbon, it has no electron pairs, so that's why it has to be this one. The shape is linear, and it's the similar rule as we've had elsewhere. It's nonpolar if the x's are the same. The x's are, in this case, the 2 reds. In our case, it's the 2 oxygens. Those are the same. So in this case, it's nonpolar. It's polar if those 2 are different. Example here of one that would be polar would be a carbon in the middle with an H on one side and an N on the other. If those 2 are different, then it's polar. And how that differs from this one here, and actually this one would be the same shape. I don't know why there's not a drawing there, but you might want to draw in something that looks just like this one right here. These two are really similar. They both have one central atom with two things attached to it. Those two things can be the same or different. But what this has is two pairs of lone electrons. So I'd recommend drawing those in like you drew the one pair up here. Draw two pairs of lone electrons here. And the example there is H2O. And actually, just to save time on getting to the Lewis structure, if we draw in H2O here, then you can see what that means by the two pairs. It's right here on the central atom, so the oxygen. So it wouldn't matter if there were lone pairs out here on the hydrogens. You were just looking on the central atom, the oxygen. It has two lone pairs of electrons plus two bonds. So that's what you've got here. This would have a lone pair, bond, bond. And so that shape is called bent, and it's always polar. And then we've got this example here. It would be just like this one, but with only one lone pair of electrons on the central atom, whereas this one has two and this one has none. And that one is also always going to be polar. So I'm going to wrap this up now, and hopefully you're comfortable with all the rest of them for the Lewis structures, the shape, and the polarity.